Good day. Welcome to Data Analytics 2 series. The topic of the lesson today is best subset in multiple regression using Frontline Solver. I'm Dr. Danielle Moret from Concordia University in Montreal, Canada. Multiple regression is widely used in all areas of research. Selecting the best predictors for our multiple regression can be done in different ways. Today, we will look at the best subset approach. To illustrate this, we will take a sample. Let us consider the following sample on variable y and predictors x1, x2, x3, and x4. We have a total of 25 observations. We would like to predict y using the predictors x1, x2, x3, and x4. We also would like to predict these three observations. There are different ways of doing that, but we will concentrate on the use of Frontline Solver in this case. Therefore, we go to Frontline to analyze the data. So we'll go to Data Mining, Predict, Linear Regression. We will identify the data that we want to analyze. We go to Data Mining, Predict, Linear Regression. We have y as the output variable, and x1, x2, x3, and x4 will be our predictors. We verify that the data range that is indicated here is what we needed for this analysis. Because we did not partition the data, all my 25 observations are part of what we call the training sets. Next. At this point, we have a few decisions that we should make. We said that we will not partition. If we did decide to partition the data, we have to use either a partition variable or random partitioning. If we select random partitioning, we often set the seed 1, 2, 3, 4, and 5. And the partitioning of the data can be done automatically, equal number in each class, in each category, or the user define. In this case, we don't partition, so we uncheck mark this part and we go back. We also have to decide if we want to rescale the data. If we rescale, we have the choice between standardization, normalization, adjusted normalization, unit norm. Each one has its own advantage. At this case here, we will not rescale the data. We'll close this window. We always like to have the ANOVA results. The ANOVA is testing the overall significance of the regression model. It's testing whether beta 1 equal beta 2 equal beta 3 equal beta 4 equals 0 all at the same time. If it is the case, there is no regression. If we can reject this hypothesis, then we claim that we conclude that at least one of the beta is different from 0. And we'll discover that in the analysis of coefficient. What is important for us at this time is the feature selection. How will we extract the variables? Should we use the backward elimination? This is the one that we are most familiar with all the variables are in the initial model, and we remove one at a time the least significant variable. It could be the forward regression. In this case, one variable is added to the model at a time. The best one is added and then the second best one. The stepwise regression is a mix of backward and forward selection, and we also have the sequential replacement. In this example, we will focus on the best subset. The best subset is going to give me, for any number of predictors, what is the best choice. If for the example where there are two predictors, what are those two predictors that give you the best results? And the maximum sample size, we don't want more, we have 4 predictors already. Next, we'd like to have a detailed report of the analysis, the summary report, the lift chart. This is another topic, but we'll come back to it in another lecture. And we want to score the data. We want to score the data that I have here in my original observations, and I want to score the new data that I have at the beginning of this example. Therefore, I must select this range, and we have it here. It is very important to note that the title of these 4 variables are identical to the titles of the original data. At this point, we say match by name, because it is the same name that we have in the original data and in the data that we want to predict. And then we finish here. Excel is giving me everything, every step that I have done. I did not want to rescale the data, so it says false. I had an intercept, true. I did not ask for the variance-covariance matrix or the multicollinearity diagnostic, so that's why it's false. I asked for an analysis of coefficients. I asked for the ANOVA, that's why it's true. I did not ask for any other diagnostic. I have selected the best subset method. The maximum size of the subset is 4, and the number of best subset for each category, I only want 1. It's giving me information about the original model. Should I have all the variables in my model? This is what the equation I would get. Minus 593 plus 2.5x1 plus 1.9x2 plus 2.6x3 minus 0.12x4. I have also the confidence interval around those coefficients. The standard error, we saw that as SB1, SB2, SB3, SB4. The t-statistics, it is the ratio of the estimate over the standard error, and the corresponding p-value. We can identify from this table here the most significant variable. The most significant predictor is the predictor which has the smallest p-value, which is here x1. If all the p-values were equal because of limitation in decimal, I can look at the t-statistics, and it would be the highest t-statistics in absolute value. So this is important to check. The ANOVA here tells me with a p-value of 2.94 times 10 to the minus 8, that is highly significant. The total under the mean square is not something that we will use. Even we don't recommend to have it. Here are the results. This is the most important 2 tables to look at. Subset 1, it says that it has only one variable, no variable. It has only one, the intercept. And where it puts 0 for x1, x2, x3, x4, that means they're not included. Subset 2, it will have an intercept and it will have the variable x1. It has determined, in the case of regression, when I have only one predictor, better have x1. It's the best among the others. Subset 3, if I have to have 2 predictors, then it should be x1 and x2. They are the best 2. It's better than x1 and x3 than x1 and x4. Subset 4, I have now, if I want to have 3 predictors, should be x1, x2, and x3, but not x4. Subset 4, then it is when I have them all my predictors, so I'm back to the original model. The second table here will help me determine which regression I will keep. Now, it is given to me with some information. Number of coefficient. This is in the first, this corresponds to the first subset where I had only the intercept. Definitely, it's not something I want to consider. The second, when it is with the intercept and x1, the sum of square residual is this number here. The CP-malo will be discussed more extensively in another lesson. Coefficient of determination, the adjusted coefficient of determination, and some quasi-probability. We will not pay too much attention to this one. In this case, we'd like to have the one that has the smallest CP-malo and the best adjusted R-square. The best CP-malo is here at 1.6, which corresponds to subset 3. It also corresponds to the adjusted R-square of 0.841, which is the highest one among the adjusted R-square. Adjusted R-square means it is adjusted for the degrees of freedom. Therefore, it is adjusted for the number of observations and the number of predictors. Excuse me. We said we need to keep subset 3. Therefore, here is subset 3. Subset 3 with variable x1 and x2. I will continue my analysis, but with the ANOVA analysis of variance, but I will not have now an extraction. So the feature is taken off. I still want to fit to predict. Therefore, I have to re-identify my prediction, which will be here. Match by name and finish. Therefore, this is my final result. It's telling me now this regression with the best 2 predictors of size 2 predictors. Here's the best one. Minus 516 plus 2.47x1, 1.85x2. We have the t-statistics, the p-value. P-value shows that both coefficients are significant at 5%. The overall ANOVA with the p-value of 6 times 10 to the minus 10 is also highly significant. We have here a prediction summary. This is something that we'll be using in other analysis too. Gives me a summary, sum of square error, mean square sum error, root mean square error, the MAD, which we will see later, it's the mean absolute deviation, and the R-square coefficient of determination. Frontline solver has predicted all the values, 25 record in my sample. It has predicted them and given me the residuals, which is y minus y hat. Residuals are useful when I will do a residual analysis to know if my final model is good. Also, we have asked to predict those 3 observations that we had. So it has predicted record 1, 2, and 3 also. Therefore, the use of this type of approach, the best subset, is very useful. We could have done similar things manually, but it will take a long time because when we have more predictors, it takes more and more time. Therefore, I hope you enjoy the best subset in multiple regression using Frontline Solver. See you next time.